Welcome to the course, Special Relativity, Electrodynamics and General Relativity. This is a course based on the book shown here, and it's a course at the level of an undergraduate physics majors course that might be taken by physics majors, math majors, and astronomers, perhaps at the third year in the American system. The book consists of 3 parts. There's a part on special relativity and electrodynamics. That's the first 10 chapters of the book, and that will be the subject of these lectures. The second part is on classical differential geometry, which leads into general relativity, the theory of gravity. Now, on the cover of the book, you see a pentagon of 5 very familiar figures in physics and mathematics. On the left-hand side, you see Carl Friedrich Gauss and his student, Riemann. Carl Friedrich Gauss, remember that among the many things that he did in mathematics, that he invented classical differential geometry. He studied 2-dimensional surfaces in 3-dimensional Euclidean space and introduced the notion of curvature. He showed that his definition of curvature was intrinsic. That means that you could measure the curvature just by the properties of the surface itself. You didn't have to know that it was embedded in 3 dimensions. That was irrelevant. All you had to do was measure distances and angles on the surface, and you could tell how much it was curved. That's critical to physics. Okay, in physics, we want intrinsic measurements of space and time. Now, Gauss was the initiator of the subject, and his quote student Riemann took the ideas and generalized them to n dimensions. Introduced the idea of the Riemann tensor, which is a generalization of the Gaussian curvature to n dimensions. And Riemann built on the discoveries of Gauss, the major discovery being that curvature was an intrinsic property of the surface, and he built his geometry just on the basis of intrinsic properties. There was no mention whatsoever of an embedding space. This made a great influence on Einstein, who was looking for laws of nature that were intrinsic. So the formulation of geometry by Riemann was essential in formulating geometry in a way that you could find intrinsic properties. On the other side of the pentagon here, we find Sir Isaac Newton, the inventor of modern physics. His Principia Mathematica was the basis of dynamics and optics and all sorts of phenomenology and basic physics of the day. We're going to study Newton's laws because we're going to start with Newton, and then we're going to see how Newton's ideas have to change in order to accommodate the ideas of relativity, the discovery that light travels at a velocity which is a invariant quantity. That is, light has the property about it travels at the speed limit in any particular frame of reference, and that quantity, the speed of light, is the same in all reference frames. An idea that is totally outside of the scope of Newtonian physics, and as a consequence makes Einsteinian space-time different from Newtonian space-time, and that's something we want to understand. Now, in this course, we're not going to follow historical developments. I'm not going to present Newtonian dynamics and mechanics the way he thought of it, but rather we're going to use hindsight and formulate it in a way that it leads naturally to the modern theory of kinematics and dynamics in relativity. Okay. Now, above Newton, we see Maxwell, okay, who took 200 years of experiments in electromagnetic phenomena and assimilated them into 8 equations, the Maxwell's equations. You know some of them. Certainly you know Gauss's law. You probably studied Ampere's law. But for us, we're going to do Ampere's law, but corrected for relativity. It's called Maxwell-Ampere's law, and it contains something that in the classical texts they call the displacement current. It's not going to be so mysterious for us because it's a consequence of relativity. He also, of course, incorporated Faraday's law as well, and we'll learn about all of that as we go. So Einstein at the top was faced with some contradictions in physics in his day. We're thinking about the times of the turn of the century, 1900. The ideas of Newton were very successful, led to all sorts of predictions that were very accurate. But then along came this theory of Maxwell about how electromagnetic waves propagate through space-time. One of the consequences of Maxwell's laws that we'll find, we will derive this, is that there's a wave equation for light, and that in this wave equation, light travels at a speed called c. We'll identify it as the speed limit of special relativity. So we have a fundamental equation with a new dimensionful parameter in it. It's the speed of light. It makes no reference whatsoever to any particular reference frame. If you look at it, and the way we'll look at it, you'll see that the speed of light is the same in every reference frame. Well, that's totally contradictory to Newton's idea of speed. Speed had to be measured relative to a particular reference frame. And if you knew it in one reference frame, you knew it in a different reference frame by knowing this relative speed between the two frames. You might have one frame being a railroad train moving at a velocity 100 meters per second. And then you might have the reference frame of stationary beings at the station of the railroad train. Okay? And so there's a 100 meter per second difference between the two frames. That should be the difference in the velocity of light measured in the two frames. But no, that was inconsistent with Maxwell's equations. He said the speed of light was the same in every frame. At the time, that caused a great conundrum because physicists wanted to hold on to the ideas of Newton because they were magnificent in predicting phenomena. And when they did that, they had to assume that Maxwell's laws were only true in one frame, and that was the rest frame of the mysterious ether. Okay, so they threw out the idea that all frames are equivalent, and they had a preferred frame. Well, we're not going to study the history of the ether or anything like that. We're going to instead think about the postulates of mechanics, both from Newton's ideas and from Einstein's ideas, and we'll proceed mathematically and physically from those bases. Now, the references in the book, talk about the ether theory and the history of the times, and you're encouraged to look at that material. But for us, we're going to do a self-contained discussion from postulates. Okay, there'll be plenty of physical intuition in this course. Don't worry about that. But there's also going to be a tight, rigorous workings from simple postulates. I'm never in this course going to pull in all sorts of phenomenology. It's very typical in textbooks to drown you in an encyclopedia of facts. That's not the idea of this textbook. This textbook is very simple, has just a few concepts, and they're developed in detail. The point of this book is to empower you. Okay, so it's not to flood you with lots of facts. It's rather to show you the foundations of mechanics, the foundations of relativity, and show you that on that basis you can make a great deal of progress. In our case, the progress will be the derivation of Maxwell's equations from the principles of relativity, plus, in our particular case, Gauss's law. Okay. So I'm just going, in this introductory lecture, just discuss the nature of the course and set up the character of the book. What's covered, what are we looking for, what might you think about in this lecture series and in this book. Okay, so we'll begin with Newton's law, Newton's world, okay, and then we'll revolutionize it to accommodate the principles of Einstein's world. Okay, the first principle that we'll deal with in Einstein's world is the fact that the laws of physics are the same in all inertial frames. Inertial frames are frames without an external force. Okay, and we've all heard of that before, and that will be a sacred principle of our proceeding. Okay, and Newton, of course, had that in his theory as well. Okay, but when we come to the second principle, that's where a deviation occurs. In Einstein's world, there is a universal speed limit. We'll call it c. Experimentally, it's about 2.9 times 10 to the 8th meter per second. And it's a universal speed limit in all inertial frames. You've heard of the Michelson-Morley experiment, okay, which gave a basis to this idea. And of course, in modern experiments, it's rediscovered every time you turn on an accelerator, for example. Okay. This difference, however, in Newton's world, there's no speed limit. Right. Okay. In Newton's day, you know, he was dealing with experiments with very pedestrian type of velocities. He didn't have fancy equipment. He didn't have a Large Hadron Collider or something to accelerate particles up to a tiny fraction of the speed of light. So for him, in his experience, there was no speed limit, and that was the character of his space-time. Now, as we develop this, again, we're not going to follow history. Newton spoke about absolute space and absolute time. Okay, we're not going to do that. We're going to just use postulate 2, that in Newton's world there's no speed limit, while in the real world, the world of Einstein, there is. Okay, and we'll see how that develops. One thing I might add, of course, is that Newton believed in the world that the laws of physics are the same in all inertial frames. That's usually referred to as the principle of relativity. So Newton was a relativist. Okay, it's just that number 2 was different between the two. By the time of 1900, there were indications that there was a speed limit, and Einstein took that perspective. He didn't refer to a speed limit. He referred to the speed of light, and the idea that was the same in all inertial frames. Now, other principles we're going to use when we do this course are these two. The first one is causality. Okay, that you can have two events in space and time, and if they're connected by a light ray, they can be causally connected. One can influence the other. Okay, if they're just nearby, okay, and can be connected by a propagating particle moving with a velocity less than the speed of light, then they can be causally connected. If, however, you know, they exist very far apart, and so at particular times, okay, and there's no time for light to propagate between them at its speed limit, then they're not causally connected, and they can just act independently. So that we have the idea of causality, and that's a critical idea in special relativity and in general relativity, and we'll utilize it. Okay. Another idea we're going to use very much in relativity is locality. That is, when we disturb a region of space-time, we disturb it locally. Okay, and then as we wait further in time, that influence can propagate out, but it takes time to do that. To express the ideas of relativity and be consistent with causality and locality, we'll see that we'll be pushed toward differential equations which are local. Okay, this is going to differ from perhaps the formulation of physics that you've had in your elementary courses, which didn't emphasize the idea of locality. But we're going to find out that it's a critical element of relativity, and it lets us put our finger on the difference between Einstein's world and Newton's world, and it's going to guide us as to how to make formulations of equations like electrodynamics in a way that we can see that they're relativistic, and in a way that we can deduce one law from another. Okay, so lots more on A and B as we go. Now, as we proceed from Newton to Einstein, let me just give you a little bit of indication of what's to come. A little summary here. In Newton, we use forces all the time, right? You've done that lots of times. You've done the simple harmonic oscillator. You've done the moon rotating around the Earth. You know forces like harmonic forces. You know gravitational forces, electrodynamic forces, and maybe you know phenomenological forces as well, like viscosity or things like that. And forces are important in Newton's. But when we move to Einstein and we think about locality and causality, we're going to be pushed in another direction. Forces are not going to be very as useful, but the concept of fields is going to become useful. So we'll be moving from electrostatic forces between separated charged particles, okay, where the electrostatic field is just a handy way of saying what the force law is between those particles, to the concept of the electromagnetic field, so that if we have two particles and one jiggles about here and it influences the electromagnetic field in its region, okay, which then grows in influence and then influences the position of the other one, we're forced to talk about fields. And we have to talk about fields with Einstein because information doesn't flow instantaneously. Okay, in Newton's world, there's no speed limit. Information can flow instantaneously, and that's the basis of his dynamics. He talks about action at a distance. He talks about action-reaction. Those ideas don't work for Einstein. They're not compatible with a speed limit. And that's an idea that we'll be developing as we go. We'll find also that in Einstein's world, energy-momentum conservation becomes a local equation, and energy, momentum, and mass become unified. Everyone knows the most famous formula in physics, E equals mc squared, and we'll be deriving that as we go. Once we have E equals mc squared, we see that energy and mass can be interchanged. We'll find that momentum and energy are aspects of the same quantity. Okay, and so we'll find that energy can be converted into mass and mass to energy. When you look at a collision of elementary particles at the Large Hadron Collider, you have a couple of protons coming in and maybe 150 projectiles coming out. Mass, energy converts into mass, and vice versa. We'll find also that very familiar features of the real world, like magnetism, are actually a consequence of relativity. Okay, we'll see that magnetism doesn't sit well in Newton's world, but it's a natural consequence in relativity. It's a velocity-dependent force. Velocity-dependent forces are unavoidable in relativity. I don't care if you're talking electrodynamics or you're talking about gravity. There's gravitomagnetic forces in gravity, okay, velocity-dependent effects, which are fundamental and must be there because of postulate 1 and 2 of relativity. So that's something important to learn. Okay. We'll find that all of Maxwell's equations are consequences of Gauss's law plus relativity. Gauss's law, the idea that a charge density locally produces an electric field, that the charge density is proportional to the divergence of the electric field. We have to state that as a covariant equation, and then taking that and adding relativity, Lorentz transformations will generate Maxwell-Ampere's law. We'll generate Faraday's law. We'll see that these laws are all mixed together by relativity. You can't have one without the other, because if you change reference frames, you generate one from the other. And we'll demonstrate that as we go. We'll find that the electromagnetic field is both electric field and magnetic field, and that they become dynamical. We'll derive a wave equation for electromagnetic fields, the fact that light propagates, and that it propagates at a speed which will be the speed limit of special relativity. We'll derive that. We won't come until the end of the course, and we'll be assuming it as we go, but you'll see that it's a derivation of special relativity. It's not an assumption. Okay, so in the next lecture, that's the end of the introduction. Okay, that tells you what we'll be doing. Okay, and I encourage you to take a look at the textbook. We'll find that getting into relativity is a conceptual challenge. Typically, when we do a derivation, we're going to come back to it and do it a second way, and maybe we'll come back and do it a third way, independent way, so that we can understand these new concepts. Some of the derivations you'll find mysterious; they won't be natural to you. But just give it some time. Just wait. I'll do it another way. For example, when we do time dilation, we're going to do it just by making a simple clock out of light and mirrors. Okay, and so that'll appeal to some of you. To others, well, that might be a little bit hocus pocus. But then wait a minute, and we'll do it visually on a Minkowski diagram, a picture of space and time. Well, maybe you don't like pictures. Maybe you like formulas. Oh, so then we'll derive it from Lorentz transformations. Okay, the generalization of Galilean transformations, which tells you how space and time transforms between two inertial frames. Lorentz transformations are symmetries of special relativity. Right? The physics in any inertial frame is the same as the physics in any other inertial frame, and the Lorentz transformations how to get from one frame to the other. So it's a symmetry, an exact symmetry. Explicit formulas there. Maybe you'll be more comfortable understanding time dilation, Lorentz contraction, and the relativity of simultaneity. The fact that clocks synchronized in one frame do not appear to be synchronized in another frame which is moving at a relative velocity v. But we'll get to all of those ideas, and then the next lecture we'll take a look at the background for all this Newton's mechanics. See you then.